Okay, if I punt a football into the air at an angle of 40 degrees with an initial velocity of 4.2 meters per second, what are the components of that vector? Right? This is the whole reason we did vector addition, is so we could look at components of launched projectiles. Okay, so I want you to think about what this motion is going to look like, and then I'll show you how we solve that out. Okay, first of all, I draw my origin, right? The ball is going to go through the air something like this. We would agree with that? Okay, so the way we look at our initial factors here, 4.2 meters per second at 40 degrees, is we zoom in on the first part of our motion. Right? We just literally zoom in on that initial launch. Okay? And so if we zoomed in on that initial launch, it would look like this. Oops. 40 degrees, 4.2 meters per second, right? And so this zoomed in section of our projectile doesn't go at that angle for very long. It's only the instant that it starts. And so when we draw this triangle, we're looking at this very, very instant that it becomes a freely falling object, that it becomes a free object. So we take this initial part of our motion, we zoom it in, and that's how now we're allowed to find the initial velocity components, right? Its initial velocity is 4.2 meters per second at this angle. We can't put velocities at angles into our kinematics equations anywhere, right? There's no place for that. In our projectile equations, there is no longer just initial velocity. What is it now? Initial velocity x and initial velocity y. Okay, so go ahead and pull out your projectile equation sheet. If you don't have that out yet, get out those projectile equations so you can be looking at them. In those projectile equations, is there a VI anywhere?
No.
No, right? This 4.2 is VI. But we can't use that anywhere. We need to use VIY and VIX. Actually, I don't like labeling that way. I like VYI on the order. VXI. Okay? We want the vertical and the horizontal components of that initial velocity. Are these objects in our kinematics projectile equations? Yes, right? That's what we need. So let's go ahead and break down that vector into VXI and VYI. VXI would be using sine or cosine. For VXI, would we use sine or cosine? Cosine, good. So I would take the hypotenuse times cosine of my angle. And for VYI, I would take my hypotenuse times sine of my angle. Do we have any questions about why it was drawn, why the triangle was drawn like north of east? Or why I chose to draw the triangle that way? Yeah, when something is launched and it doesn't give us a cardinal direction, we just assume it was launched forward, right, and through the air. So when in doubt, like when it's not given a cardinal direction, we're just going to draw it going up and forward, right, because that's the most common thing. Okay, so do we have an answer for VXI and VYI? 3.21 for X?
2.22.
Okay. And for Y, what was it? 2.7. Okay. 2.7. We agree with both of those? Yes? No? You got a negative? Enough times over my years of teaching that 4.2 will get plugged in if you don't cognizantly get rid of it. Okay? So, let's practice a full problem now. Okay? A football is kicked at an angle of 37 degrees with a velocity of 20 meters per second. Calculate the maximum height and the time of travel before it hits the ground again. Okay? I'm going to give you a minute to get written down what you need to, and then we will start working together. Okay, 20 meters per second is the hypotenuse of our initial velocity. Bless you. And 37 degrees was the initial launch angle. Okay? That object will continue to go through the air, and it will continue to fall. Bless you. Okay? And I'll kind of redraw that once we get close to that part of the problem. But the very first thing we do with the launched projectile is what? What's the very first thing we should do when we get a velocity at an angle? We find the components, right? We break down the vector. That has to be the first thing you do for a launched projectile. So I'm going to say Vxi and Vyi. Also, why do you think I'm not just saying, okay, the x velocity is this and the y velocity is this? Why can't I just label it with x and y?
They're just different vectors.
What would x lead me to believe I'm solving for? Displacement, right? xf is the variable for displacement. So you can't, unfortunately, unless you are super laser focused on what you're doing, you can't just be lazy with your variables. You've got to label them correctly. So Vxi would use cosine, so I'd say 20 times cosine of 37 and 20 of sine of 37. Do you already have those solved? Sorry, am I going too slow?
15.97.
Okay. Is it for my x?
Yep.
Okay. 15 point what?
97.
Okay, I'm going to go ahead and round up to 16. And my y component is 12.
Yeah.
Okay. So now, I think for your own sake, right, I'm crossing out my 20, crossing out my 37, like I'm done with that part of the motion. Okay. I'm also, for our purposes right now, going to just redraw it, so when we talk about it, we'll have a little bit of frame of reference. So I'm just going to draw a little picture over here. You don't have to draw that. You can. We're going to talk through what it's going to end up looking like in a second here. We have two parts to the problem that we need to solve: the maximum height and the time of travel before it hits the ground again. So we want to know the maximum height, which is right here, right? Peak height. We want to find out how high it's going. And then we want to find out the total time. Do we agree? All right, so let's do peak height first. Okay, I'm going to come over here and say we're solving for peak height first. All right, that's just how I abbreviate peak height. Okay, or maximum height. Is peak height a vertical scenario or a horizontal scenario? We need to be focusing on vertical, right? So we know our initial vertical velocity is 12. What do we know about our final vertical velocity at peak height?
0.
It's 0. So at peak height, we know that VYF is 0. Okay? We know our VYI is 12. We need to solve for Y final. Right? What equation do you think we can be using to help me solve for YF? The third one, right? Because I don't have time yet. So it's got to be my third kinematics equation. We agree with that? Okay. So that would be 0 squared equals 12 squared plus 2 times negative 9.8 times Y final. Okay. Why did I just plug in Y final? Why not delta Y? Exactly. Y initial is always 0. So if we're just taking Y final minus 0, there's no need for us to include that. Okay. So if I do the math, that would give me negative 144 equals negative 19.6 times Y final. Okay. All I did with that is I took my 12 squared, which is 144. I had to subtract it to the other side because there's a plus sign right there. Right, that's a plus sign. So I subtract it over there. And then these terms are all multiplied by each other. So I still have negative 19.6 times Y final. So can I add 19.6 over to the other side? No, I have to be dividing that over. So, what'd you get? Oh, why is this one negative? The 144 negative? This one, because my negative 9.8. So 2 times negative 9.8. That's okay.
So then you just divide.
I divide negative 144 by negative 19.6. And Jimmy, you said we got, okay, so 7.34 meters. Okay, so that tells me my kick gets 7.3 meters off the ground. Okay, now I've answered.
That's our YF.
That's our YF. That's my maximum height. So I've answered the first part of my question. All right, second part of my question asks for total time. And so there's 2 ways to solve this. And we talked about this when we did vertical kinematics. We said we can use our shortcut method, which means to solve for time on the way up, and then do what? Multiply by 2, because it takes the same amount of time on the way down, right? That method works here because my object is going to start and end at the same height, right? It is symmetrical motion. So that shortcut method of solving for half time and then then multiplying by 2, that works here. It applies here. We will go through a couple problems in which it doesn't apply, and so we'll have to do something different. Right? If we launch it off a cliff or it lands somewhere different. Yes. But for right now, that method will work. So if I solve for time, I'm going to solve just for half time first, and then I'll multiply it by 2. Okay? At half its path, we're looking again just right here. So we know that VYF equals 0 still at its peak height. And we know all of these things still. So we can just use our first kinematics equation to help us solve for time, right? To peak height. So I would say 0 equals VYI plus negative 9.8 times T. Is everyone seeing where I got that equation from and the reasoning behind that?
Where?
That is our first kinematics equation, VYF. And the reason I chose that one, I could have also used my second one because I have my peak height. I know how high it went at that point. But for simplicity's sake, I'm just going to use that first one. We know that VYF is 0 at its peak height only. And so since it's symmetrical motion, we can solve for the amount of time it takes to go up because it will be the exact same amount of time to go down. Does that kind of make sense?
I was just wondering what was in front of this.
Oh, I'm sorry. Right, that's just an arrow. I was just saying we're just solving for half time, so this is how we're doing it. Sorry. Okay, so 12 divided by 9.8 is 1.22. Right, 1.22 seconds. This is only half the time. That's only the time it takes to come up. So I multiply that by 2, and I say it's going to be in the air a total of 2.44 seconds. Okay.
Then we're done.
Then we've answered both parts of our question. Yeah. The thing that I really want you to understand about projectile problems is that there are several ways to get to our final answer. We could have used several steps of equations to get to our final answer. You have to just be able to think through what parts of the motion are you concerning yourself with, right? Where are you going to go? So you can go from start to finish several different ways, right? Just because I'm showing you this way doesn't mean it's the only way it can be done. So if you are thinking in a different way, right, you can do your sets of equations and get to your final answer and still be fine. Okay? Like even for our last one, we could have solved for time using our second kinematics equation and saying our initial height and our final height were both 0. We would have had to use the quadratic formula, but you could have done it. Okay? So there's lots of different ways we can get to our final answer. So I don't want you to try to memorize like we have to use this equation in this scenario and all that kind of stuff. That's not the case. Okay? Questions about that one, sorry, before we move on? Okay. All right, now suppose the same football was punted from a distance of 1 meter off the ground. How far did the ball travel before hitting the ground? So we're looking at the same initial scenario, but now, like we said, we're not starting and ending at the same height. Okay, so this is what it looks like. Here's my origin. Just launch through the air, and it's going to land down here. Okay, so here's the ground. Oops. Here's the ground. There's a difference here of 1 meter.
Would you just add to YF 1?
You can't add that to YF, no, because we're not looking for YF, we're looking for XF. How far did it travel? Right? How far horizontally did it travel? And so YF that we solved for told us how high it went. It didn't say anything about falling back to the ground that extra meter. So it's not going to go any higher, it's just going to fall longer.
Wait. If it takes...
Initial velocity components we already know. We know Vxi is still 16. We know Vyi is still 12. Right? Did I list those right or did I mix them up? Was it X that was 16 and Y that was 12? Okay. So now we've got this issue of our Y final for our total path is now -1. Right? My Y final for the whole path of my motion is now -1 meters. And so the time that it took, wait, sorry, I'm seeing some mixed up faces there.
Wait, what's Y?
My final displacement of my object from the beginning where it started to the end of its motion. So from here to here, there is a difference of -1 meters. My equation will take into account the fact that it's going to go up and it's going to come back down and it's going to land 1 meter below where it started. Okay, so my equation does all of that work.
7.3.
YF was 7.3, but that was only at peak height. Here, I'm not concerned at all about peak height because my question asks me about the total motion. So I don't care in this scenario how high it went off the ground.
But this peak height is still 7.
Peak height would still be 7.34.
So if in the second half of it went down farther, wouldn't that take more?
It takes more time, right? So the time that we solve for first is no longer applicable. It will be in the air longer than 2.44 seconds, which means we have to resolve for time, and then that will allow us to solve for X final.
Wait, so is it, because like it's not going like below the ground, so it was like a meter off the ground?
Right, like when it contacted his foot was a meter off the ground, right? That's what it's saying.
And 7.
Right, like if you kick the football starts on the ground. When you punt the football,
Yeah.
right, it's starting off the ground. So here it's going to land on the ground. So even though, yes, I'm sorry, I drew the ground here. It's technically it's foot height. Okay? So we need to solve, our final goal here is to solve for XF. Okay? Final goal, how far did it travel, is XF. And we know if we want to solve for XF, we need to have, where is it? We want to solve for XF, we need to have Vxi, which we already have, and we have to have, look at your equation sheet, what else do we need to have? T. We need to have T. And so like we already discussed, the 2.44 seconds is no longer applicable. It's going to take just a little bit longer because it's got to fall an extra meter. Okay, so we need to solve for time. Which means if we have to solve for time, we need to go back to our Y equations. Time is the one connector between our two sets of equations.
So on my equations sheet, I have...
Okay. When we want to solve for time out of these scenarios, usually, most often, we use that second vertical equation.
The second.
Y final equals. That's usually what we use to solve for that. And that's what we'll do in this scenario.
Wait, could we not use the first?
No, because we don't know what VYF is at the end of our motion.
No, the first kinematic. So VF equals VI.
No, because that doesn't take into account the differences between X and Y. Right? We have to have the difference in X and Y. For projectile motion, we analyze horizontal motion and vertical motion totally separately. So those regular kinematics are not applicable for us in this chapter. We have to use the projectile ones. Okay, so let's say we use our second vertical equation. Y final equals Y initial plus Vyi times T plus 1/2 AT squared. Okay, Y final is -1, 0. Vyi is 12 times T plus 1/2 -9.8 times T squared. Do you see where I'm heading with this? For non-symmetrical motion, that's I'm sorry, I can't find the word I want. These are the types of questions. Non-symmetrical motion is when we have to use the quadratic formula. Right? That's the situation in which we would use the quadratic formula, non-symmetric motion. Okay, here's where my equation is. I have a T, and I have a t squared.
Yeah.
Right? That means I need to use my quadratic. So I'm going to rearrange this equation to get it into quadratic. We can't do the first one because we don't know VYF. So remember the way you... I'm going to finish this and then I'll remind you how to bypass the quadratic. Okay. So here I have my A term goes with t squared. So I'm going to put that first. Negative 4.9 t squared. My B term goes second, 12 times t. My C term, which I would need to move to the other side, because quadratic formula always gets set equal to 0, would be a plus 1. Right, that's my C term. I need to move it over. Does that make sense? The quadratic formula always has to be set equal to 0. So I'd move that to the other side. That gives me a plus 1. So now here's my A, my B, and my C terms. Okay. This is how I always do these problems, but that does not mean you have to. So here are 2 ways you could bypass the quadratic. 2 ways. So listen up. If you hate the quadratic, you need to listen. I'm not going to walk you through it, but you can listen. The first way would be to solve for how fast, what is VYF at this point? What is VYF at this point? You could use your third kinematics equation to solve for VYF, and then you could go use the first equation to solve for time. Right, that's a way you could bypass the quadratic. Use your third kinematics to solve for VYF, and then use your first equation to solve for time. Second way Michael gave as an option, you could just find the time from peak height, using your starting velocity as 0, and then finding the time to solve for that and adding it to the half time we solved for first. Right? That requires a little higher thinking, but it's an option. So if we looked at the time it takes from here down, our initial velocity now is 0, because we know it stops at its peak height. So now we go 0 to finding what our time is, using our third kinematic. No, you don't know VYF either. You'd have to solve for VYF for that one too.
You just, because you already know the height.
Wait, so
Because I-
for the
one, two,
kinematic.
So you could use your second. I see what you're saying.
For the quadratic, you got 2.5.
I got, after the quadratic, I got 2.5. Okay, do we see how there's lots of options to get to our final answer? Right? I use this method. I have the quadratic formula programmed in my calculator, so it goes faster. So that's why this method is faster for me. But you can use lots of different ways to get to your final answer. Okay? Questions? We still haven't solved for x yet, sorry. Last step here would be to take VXI times 2.53 and get how far it traveled. All right, this is very similar to the first problem we did. It asks for max height and flight of the ball. Okay. When it says to the horizontal, all that means is that here's our horizontal. It's launched 66 degrees up from that. So it's the same way we've been drawing it. Okay. Right, or if you're not sure what sets of equations to use, please ask. But this is a non-symmetrical one.
Wait. Wait.
I plugged it into the quadratic.
I forgot to put around VSI to